Today we'll cover level flight performance data reduction. For this lab, you'll need airspeed and altitude off the gauges in the second or third row, outside air temperature on the gauge above the pilot, manifold pressure, RPM, and fuel quantity. Step 1 is to apply corrections to airspeed and altitude data. For this example test point, we recorded an airspeed of 135 miles per hour and a pressure altitude of 5,000 feet. We'll take the indicated airspeed and apply our instrument correction and position corrections off the curves we generated from Lab 1 to arrive at a calibrated airspeed of 129.8 miles per hour. We'll take our indicated pressure altitude of 5,000 feet and add the instrument correction of 40 feet to arrive at an instrument corrected pressure altitude of 5,040 feet. Step 2 is to calculate brake horsepower at our test day condition. First, we'll calculate brake horsepower at a standard day and then convert it to test day using the square root of the temperature ratios. To get our brake horsepower for standard day, we'll follow these 4 steps on the engine chart for the Cherokee 6. Step 1 is to locate point A on the full throttle altitude curve for our manifold pressure and RPM. This is the altitude side of the engine chart, and that's where we start. We'll take 24 inches of manifold pressure and 2,700 RPM and find those grid lines on the chart. Here's grid lines for manifold pressure of 20, 22, and then the red line is 24. Here's the grid lines for RPM, and this green one here is the RPM of 2,700. Those green line and the red line intersect at point A. Step 2 is to locate B on the sea level side of the curve for the same manifold pressure and RPM. In this case, 24 inches of manifold pressure line is vertical, and we follow that up till it hits the 2,700 RPM line, and that's point B. We'll then take point B and extend it horizontally until it intersects the altitude side and call that point C. We'll take point C and connect it with a line through point A and continue the line even past where the grid lines stop. Once we have this line, we'll take our pressure altitude of 5,000 feet and follow the purple line where it intersects that line we just drew. That's point D, and then we'll follow that over here and read off our standard day brake horsepower, in this case 224 horsepower. Once we have that, we'll multiply by the square root of the temperature ratio. In the numerator is the standard temperature for 5,000 feet. In this case, it's 5 degrees Celsius divided by the temperature we recorded at altitude, which is 14 degrees Celsius. So we were hotter than standard day. And put that into Kelvin. And once we have that ratio, take the square root of that, multiply by our standard brake horsepower of 224, and we see that our test day brake horsepower is 220.5. Step 3 is to calculate density ratio using the equations we saw in our pedostatics calibration for sigma and theta. So plug in instrument corrected pressure altitude from step 1, OAT from our card, and we'll arrive at a density ratio of 0.8337. Step 4 is to calculate the weight ratio, which is our test weight divided by a standard weight. Our test weight is whatever our takeoff weight is minus our fuel burn. In this case, that was 3,299 pounds. The standard weight is whatever the aircraft manufacturer wishes to certify as the gross weight of an aircraft. For the Cherokee 6, that's 3,400 pounds. So the weight ratio is 0.97. Step 5 will calculate VIW, instrument and weight corrected airspeed. Here's the equation, and for the speeds that we fly with the Cherokee 6, calibrated is nearly identical to equivalent, so we'll use our calibrated airspeed of 129.8 divided by the square root of the weight ratio to give us a VIW value of 131.8 miles per hour. To calculate instrument and weight corrected power, PIW, we'll use this equation, taking the brake horsepower test that we calculated of 220.5 times the square root of the density ratio divided by the weight ratio raised to the 1.5. For this example, PIW equals 210.6 horsepower. We'll then want to repeat all those calculations for every point that we flew on our level flight performance lab, knowing that you're going to have to go to that engine chart with the temperature, manifold pressure, and RPM and calculate a brake horsepower for the test day. So once you have all the data calculated for each point in our level flight lab, you'll have VIW versus PIW. You'll then generate a plot with VIW on the x-axis, PIW on the y-axis. And here's the plot. Once we have the data, we'll want to fare a curve through the data, or use Microsoft Excel in this case to generate a curve. And this is the equation of the second order curve fit that we used Microsoft Excel to represent our data. Next, we'll want to plot our maximum achievable manifold pressure for the two altitudes we flew. We got level flight data at two altitudes, one around 5,000 feet and one around 2,000 feet. And we start each point, in this case at 5,000 feet, with the maximum achievable manifold pressure. So in this case, it was 24 inches of mercury. Then when we drop down to 2,000 feet, our maximum achievable manifold pressure was 27. So now we have 2 points. We can generate a line that now gives us data for the maximum achievable manifold pressure at any pressure altitude we need. Next, we'll calculate density altitude data for standard weight and standard day. To do this, on a standard day, density altitude and pressure altitude are equal. So I'm just going to select altitudes at a given interval. I chose every 2,000 feet. So this will be pressure altitude and density altitude. It's the same on a standard day. Once I have the altitude, I'm going to use that curve fit I just showed you to generate what the maximum achievable manifold pressure was for that given altitude. So this is my curve fit from the previous graph, and I'll use that to calculate the maximum achievable manifold pressure for this altitude. Once I have that data, I'll go to my engine chart and calculate the standard day brake horsepower with that manifold pressure. And so here we have 260 and so on for this data is our brake horsepower for standard day. We'll also calculate the square root of the density ratio on a standard day for all those altitudes. And next we'll calculate PIW using our equation, which is our brake horsepower for standard day times the square root of sigma, our density ratio. And in this case, our weight ratio is the standard weight over the standard weight, or 1 to the 1.5. So our PIW data here is just really the brake horsepower for standard day multiplied by the square root of sigma, or these two columns multiplied by each other to give us PIW. Once we have PIW, we're going to use our curve fit from our PIW VIW plot to back out for a given PIW what the associated VIW is. So you'll have to use the quadratic formula to calculate VIW. So that will be this column of data. Once we have VIW, we'll want to convert that to true airspeed by dividing by the square root of the density ratio using this equation. So that's the true airspeed data. So what I've shown you here is all the calculations for 100% power. I then want to generate data for 75% power, 65% power, and 55% power. To do that, I'd simply take my maximum horsepower at sea level, which is 260, multiply it by 0.75, and I get 195. That horsepower will be the same then for all altitudes. Density ratio, or the square root of density ratio, will be the same as this data for the same altitudes. And then I'll use the same equations to get PIW, use my curve fit to get VIW, and then use the calculation to calculate true airspeed as shown here using this equation. I'll repeat that for 65% power and 55% power. Again, 65% power is 0.65 times 260, and that gives me 169. 55% horsepower is 0.55 times 260, and that gives me 143. And the rest of the algorithms and data analysis is what we've talked about. Once you have this data, you'll then generate a plot of true airspeed versus density altitude. And you'll have one graph for 100% power, one graph for 75% power, 65% power, and 55% power. And this is what that looks like. So here's our 100% power. That's the most we can get. So that's kind of forms an outer bound. And then we've taken our 75% power data, our 65% power data, and our 55% power data. Normally you'd expect this to be a line like this. In this case, the slope's a little bit suspect, but then again, our data was at the lower part of the PIW, VIW curve where we didn't have as much data points.